So, since the time of John Dalton, scientists assumed that all of the atoms of a given element had the same mass. The discovery of isotopes required development of a method to represent the different nuclides or isotopes of the same element. So, what we're going to do is we're going to use symbols that help us with display the information about that isotope. So, the symbols that you're going to see are here. And so when we talk about this, the symbol kind of at the top would be the mass number. And this is the total number of protons and neutrons in the nucleus. Okay. Now, the bottom number is the atomic number, and this is the number of the protons in the nucleus. It determines the identity of the element. Right? And it's also found on the periodic table. So, for example, if you look at the periodic table and you look at gold, you're going to see gold is the 79th element. There are 79 protons in gold. In silver, silver is the 47th element. There are 47 protons in silver. These are the atomic numbers. Then you're going to see the element symbol. This is just the 1 or 2 letter symbol. To identify the type of atom. So, this is how we show isotopes. There are the other ways to show isotopes as well. Go to the next slide. I also want to define isotopes. Isotopes are the same element, which means they have the same number of protons, but a different number of neutrons. So, for example, we can see this with carbon. Carbon has all 6 protons, and it's got all 6 electrons, but it has a different number of neutrons here. And you can see the symbol here. Now, I want to point something out here when we're looking at carbon. So if we have 11 carbon here, we would also have 6. Sometimes that bottom number is left off because it's understood, right? But sometimes it's put on there. So you can see carbon written like this, that isotope. You can see it written like this, or you can see it written as carbon 11, where all of those are the mass numbers, where the 11 is the mass number, and that's all the different places you can put it. Here, people believe that you can look at the periodic table and figure out the atomic number is 6 for carbon, right? So, I would like for us to do some examples. So a good example is how many protons, neutrons, and electrons are present in a single atom of the following. So we have bromine 79 here. So when we think about bromine 79, we need to figure out the number of protons. And to figure out the number of protons, we need to go to the periodic table and look at bromine. So if we go to the periodic table and we look at bromine and we see a 35 there for the atomic number, this is the number of protons. So there are 35 protons there. Now, there is no charge on bromine. So what do I mean by that? There's not a negative there, there's not a positive up top. If there's not a negative or a positive, that's a neutral atom. And if it's a neutral atom, the electrons should equal the protons because, right, protons have a +1 charge, electrons have a -1 charge, and if this overall has no charge, when you add these together, they would equal 0. Now, so here's the sticking point. We need to figure out the number of neutrons. So to figure out the number of neutrons, we need to take the mass number and subtract the atomic number. So the mass number here is 79. We look at the periodic table for the atomic number, that's 35, and that gives us 44 neutrons. Okay. Now there are 2 more examples here, and so one of the things you might consider doing is trying to work these examples. Pause the screencast, try to work these examples, and then come back and check your work. So if you are going to do that, now would be the time. So let's look at bromine here. This is bromine 81. It's going to have the same number of protons. It's going to have 35 and the same number of electrons because there's no charge, 35. We come over here and look at the neutrons, and again, we're going to take the mass number, which is 81 in this instance, and subtract the atomic number, which is 35, and that gives us 46 neutrons. Now, I want to point out A and B here, these have the same number of protons. They're the same element. They're both bromine, but a different number of neutrons. These are isotopes. Okay. Then just one more example, iron 56. If we go and look at the periodic table of iron, we find that it's the 26th element, so there's a 26 there. We would say, great, that's our number of protons. There's no charge, so our number of electrons are 26. And then for the neutrons, we are going to take the mass number, which is 56, and subtract the atomic number, which is 26, and that gives us 30. Now, how have isotopes kind of revolutionized art? Well, one of the things that has happened has been carbon dating. So with carbon dating, it involves the isotope carbon-14, and most of what is found in nature is carbon-12, but carbon-14, we have really very specific amounts of carbon-14 that we can measure that can tell us the age of an object, as long as it was once living at some time, okay? So one of the places we've seen this is the Shroud of Turin. So the Shroud of Turin is a centuries-old cloth. It's made from linen, so it's a linen cloth. So linen was once alive, so we can use carbon dating for that. Historical records show that it first kind of popped up in 1357 in southern France, and then of course it made its way to Italy. Now, it's believed to be the shroud that covered Jesus's body. Right? And so you can see the image of a man here within the shroud. You can see the face there. You can also see the image of a body here when you look at the shroud in its totality. Okay? So carbon dating came along, which can date this. And so in 1988, there were 3 laboratories that independently dated this. And it was a blind test. They didn't know exactly what they were testing. They were just testing the different samples. So each lab was given 4 samples. And the 3 laboratories, one was Oxford, one was a lab in Zurich, and one was a lab in Arizona, right? And all 3 of the labs showed that the actual year, or the actual age, was somewhere between 1260 to 1390, right? With 95% confidence. And so given this, this was a shroud that probably covered some person's body, but it doesn't date to the time period where Jesus lived, right? And so they could say then that, hey, look, this art was not as old as we thought it was. So carbon dating with isotopes has been particularly helpful, dating historical artifacts as well as art pieces. Now, we talked a lot about our chemistry intro. I would like to talk about kind of some ancient art. So we've talked about how chemistry got started, but if we talk about ancient materials and ancient art, right, art has been really important to ancient civilizations. This is these are some images that were from a cave. This cave system is called the Lascaux Caves. These were discovered accidentally in the 1930s, 1940s in South France by 4 boys. The boys were 13 to 18 years old, and a dog called Robot. And so they explored these caves and were just absolutely amazed by the art that they found. So they found approximately 17,000-year-old cave drawings. Okay. So what are these? Well, these chemical compounds are the pigments that were used. These, of course, are the pigments of Earth. So they're reds and browns and blacks. The black a lot of times was soot or manganese oxide. And then the red is red ochre, which is an iron complex. Now there's also yellow ochre as well. This is an image of the yellow and red ochre from the region of France called Roussillon. Right. And so this is a small French village, but they have ochre fields there. You can buy the ochre pigment. But one of the things that's kind of interesting is that all of the houses kind of in this small village are made in kind of that red ochre color as well, because it's what's there. So ochre generally is made of iron, right, in some kind of complex. Now, so we're in Europe, and art is really, we've got ancient art materials in Europe, but one of the things that I think is really interesting is that we find this all over the globe independently. So ancient materials in the Tiwi Islands, right, at the northern tip of Australia, Aboriginal populations used red ochre in sacred ceremonies. So they also used red ochre. Right, and there's a lot of kind of background behind this. So young men would take a pilgrimage to get the sacred red pigment. It would be approximately 1,000 miles. There's some tribes that believe that red was so dangerous that could only be seen by certain men and never by women, and people could be killed if they saw it accidentally. And so maybe the question that you ask, which is a great question, is why is that so sacred? Well, that's still a tribal secret, so it's not something that we know. Red ochre is also used throughout Africa. In South Africa, within the last 10 years, they found an 80,000-year-old paint kit with shells as bowls that still had paint in it. So all throughout the world, right, pigments and art and ancient peoples were creating, which I think is pretty amazing. Other ancient materials that were used were seashells eggs and pearls, right? And so if we think about seashells, we think about cameos a lot of times. So if you've seen a cameo necklace, that's carved out of seashells. And so you can see here's the seashells, the raw material. There is the person that is doing the carving of the cameos, and then there's the finished product. We also have ancient materials out of limestone and marble and calcite and argonite, which a lot of times we think of those as minerals. Here's some of the raw materials. They're found in cave systems, so we see those, of course, in stalactites and stalagmites. But when we start to think about art with them, they are, a lot of our carved marble statues, right, are from that marble. The Taj Mahal is out of calcium carbonate, so in marble, and so you can see that these are, of course, two really beautiful pieces of art. So these were common ancient materials that people used for art. Again, red ochre, calcium carbonate, those were the big materials that we saw.